Hey, hello guys. So in this project, we address a key challenge in modern mining operations to figure out how autonomous vehicles interact safely and efficiently with human-driven vehicles. So current autonomous haul trucks are often designed to behave conservatively, treating human drivers as unpredictable obstacles. While this maximize safety, it can also slow down traffic flow and reduce operation throughput. So our aim is to develop a foundation for human-aware autonomous control, where autonomous vehicles can anticipate human behavior instead of wait, just let me. Yeah, so they can predict human behavior instead of just simply avoiding them. So to study this interaction, we build a high-fidelity virtual reality driving simulator using Unreal Engine 5.4. And this simulator replicates realistic open pit mining environment, road geometries, traffic controls, and track behaviors. Inside this control environment, human participants completed driving subtasks well equipped with psychological sensors like EMG, IMU, heart rate, and eye tracking for pupil diameter. And their self-reported psychological states, their trust, stress, attention, and workload were collected throughout the experiment. Our ultimate goal is to understand how these psychological markers relate to human decision in mixed traffic mining scenarios. This understanding lays the groundwork for future autonomous systems that can operate safely yet more efficiently in human-dense environment. Okay.
Okay, so moving on to the simulator and the experiment design for this capstone project. So a core part of the project is to build a realistic and reproducible VR-based driving simulator. It is tailored specifically for mining traffic. So we designed an entire virtual site with a compact open pit layout, incorporating haul roads, roam pad, and signalized intersections. So all assets, traffic controls, and environmental markers were constructed using the Unreal Engine's blueprint system. So there will be two vehicle types. So two vehicle types were implemented. So a participant-driven SUV and multiple autonomous haul trucks. So we built two autonomy frameworks. So one is a spline following controller for routine path tracking, and a more adaptive PD-based vehicle following controller capable of adjusting throttle and braking dynamically based on closing distance and time to collision predictions. So the human experiment consisted of four repetitions, each containing four subtasks representing real mining interactions. Yeah, just the task that I mentioned before. So between those subtasks, participants completed questionnaires on trust, stress, attention, and workload. So during driving, we will collect synchronized physiological data from EMG, IMU, heart rate, and pupil diameter sensors. These experimental structure provide consistent time-aligned multimodal data across comparable driving conditions, forming a robust foundation for behavioral modeling. Yep.
So moving on to the data processing and modeling sector. So in order to convert the multimodal physiological data into meaningful behavior insights, we developed an end-to-end data-driven estimation framework. So essentially, all sensors were unified and merged together, and then we computed window-level features such as means and standard deviation, and later then we aggregated them into subtask level summaries aligned with questionnaire labels. So each psychological construct, like trust, stress, attention, and workload, was modeled using logistic regression. Our results show that trust and stress were the most reliably predicted states. Notably, the standard deviation of left forearm EMG was the strongest prediction of trust, suggesting behavioral attention patterns influenced how participants perceive autonomous trucks. Similarly, the standard deviation is the most informative predictor of stress, aligning with established links between pupil dilation and arousal. These findings demonstrate that wearable sensors can provide meaningful real-time insights into human affective states during safety-critical driving. Such insight is valuable for designing autonomous vehicle controllers that respond intelligently to human behavior, supporting safe and more efficient mining operations. Thanks.